One, two, three. Good day, everyone. My name is John Jericho ROC from BIT2K, here to explain to you things you need to know about manifold absolute pressure sensor. But first, what is a MAP sensor? The manifold absolute pressure sensor provides instantaneous manifold pressure information to the engine's electronic control unit. The data is used to calculate air density and determine the engine's air mass flow rate, which in turn determines the required fuel metering for optimum combustion and influence the advance or retard of ignition timing. Purpose of a MAP sensor. The manifold absolute pressure sensor reads the amount of pressure or vacuum, also called engine load, in the intake manifold, where outside air is divided up in proper amounts and distributed to each cylinder. This pressure reading is shared with the engine control module to determine how much fuel needs to be fed to each cylinder, as well as to determine ignition timing. A fully functioning map sensor is necessary to maintain the right combination of acceleration, fuel economy, emissions, and ignition smoothness. When the throttle is wide open and air is rushing into the intake manifold, causing a drop in the pressure, the map sensor signals the engine computer to send more fuel. When the throttle closes, pressure rises and reading from the map sensor tells the computer to reduce the amount of fuel going into the engine. So in this part, it's pretty self-explanatory that an intake manifold normally has pressure at idle because if you have remember you have a flap in the throttle body that restricts the air, and only the idle jets are the ones that are responsible for keeping the engine at idle. So once you open that throttle plate, air will come rushing in and the pressure vacuum will suddenly drop, which signals the map sensor to send more fuel to each cylinder. And vice versa, when you close the throttle plate, the vacuum will return in the intake manifold. So in here you can see most of the variables. Credits to Engineering Explained. This is where I mostly get my data from. So absolute pressure inside the intake manifold. So if the absolute pressure increases, it means you need to send more fuel. And again, if the pressure decreases, you need to send less fuel because the absolute pressure is how the ECU interprets the pressure from the outside of the engine from the inside of the intake manifold. And air temperature now, the reason why this is inverted because as we all know, hot air is less dense, meaning there is less oxygen, which can mean there is less oxygen that can be mixed in the fuel. So the fuel is decreased, but the when the air coming in is cold, which is more compact and has more oxygen, of course you would need to increase the fuel ratio. And again, engine speed, this is pretty self-explanatory. When the engine is in a high RPM, you need more fuel because they're spinning more faster. And when it's in decrease and there's less rotation, less fuel is being sent. A fuel-injected engine may alternatively use a mass airflow sensor to detect the intake airflow. A typical naturally aspirated engine configuration employs one or the other, whereas forced induction engine typically use both a MAP sensor on the cold air intake leading to the turbo and a MAP sensor on the intake track post-turbo before the throttle body on the intake manifold. So in here it said that most naturally aspirated engines use only a most naturally aspirated engines use only mass airflow sensors. There you go. And when it comes to turbo type engines, they use usually a mix of both, which is the mass airflow and the manifold absolute pressure, where the mass airflow sensor is connected in the cold air intake. This is the part where after going to the intercooler or after going to the turbo, depending on the setup, that's where it's connected. Pretty much like how the mass airflow sensor is connected right in between the intake manifold and the car air purifier of the engine. And where the manifold absolute pressure is, as always, connected in the intake manifold. There are two basic types of map sensors: analog and digital. With an analog sensor, return signal voltage increase as the throttle opens and vacuum drops. In other words, voltage and pressure are proportional. Sensor voltage typically varies from 1 volt at idle to 5 volts during wide open throttle. An analog sensor produces a traditional DC waveform pattern. So you can see, so I mean, so as we have read, it means that a analog type is just like in the previous lesson, the throttle position sensor only gives voltage signals to the ECU to determine whether the pressure drops or increased in the intake manifold. On the other hand, digital sensor produce an on-off signal that can be viewed as a square waveform pattern. The frequency of the signal decreases as the throttle opens and vacuum drops. At idle, the map sensor output may be only 100 Hz, where at wide open throttle it may be as high as 150 Hz. So, unlike in the analog, the digital signal path, the digital map sensor can be viewed as a square waveform pattern, pretty much like a Hall effect type in the TPS as previous lesson also. And this time, instead of a pressure, it sends the pressure and sends the signal in an on and off form instead of a direct current voltage. So it's much more easier for the reader to analyze the pattern, as it's not a up and down pattern, more of a uniform up and then sudden down, like that. Construction of a map sensor. The pressure sensor uses a pressure chip for pressure measurements, and the pressure chip integrates a Wheatstone bridge on a silicone diaphragm that can undergo pressure deformation. The pressure chip is the core of the pressure sensor. All major manufacturers of pressure sensors have their own pressure chip. So here is the pressure sensor chip, or pressure chip to be exact, and circuit chip. Okay. Some are directly produced by sensor manufacturers. Some are dedicated chips, ASC, produced by outsourcing, and the other is to directly purchase general purpose chips from professional chip manufacturers. Chips directly produced by sensor manufacturers or customized ASC chips are generally only used in their own product. So there are many types of chip, but I think the most used are outsourcing. There you go. Such chips are highly integrated, often using pressure chips, amplifying circuits, signal processing chips, EMC protection circuits, and those used to calibrate sensor output curves. ROM is integrated on a chip. The whole sensor is a chip, and the chip is connected to the pin of the connector through a lead. Some other manufacturers of map sensors use general purpose pressure chips and they integrate the pressure chip, EMC protection circuit, and other peripheral circuits and connector pins through the PCR board. As shown in the picture below, the pressure chip is mounted on the back of the PCB. The PCB is a double-sided PCB board. So, unlike in the first one, which the chip sensor and the main chip to interpret the signal in is separated. In here, the sensor chip is directly embedded in the PCB board. So there are also two types of map sensor. The first one we're going to see is the varistor map sensor. The composition of the semiconductor varistor map sensor is shown in the picture below. There is a silicon diaphragm in the pressure conversion element of the sensor, and the pressure and deformation of the silicon diaphragm will generate a corresponding voltage signal. So more of explanation here later on the operation, but mostly this is what a normal map sensor looks like. This is the part where it's connected in the intake manifold, and here's the outlet. Usually this is a part 3 pin or 4 pin depending of the make of the map sensor, which I will explain also later. Here are the parts. You can see it. You can pause the video to see it. Okay. Next, varistor map sensor. One side of the silicone diaphragm is vacuum and the other side introduces the pressure of the intake pipe. When the pressure in the intake pipe changes, the deformation of the silicone diaphragm will change according to the voltage signal corresponding to the intake pressure is generated. Greater the intake pressure, the greater the deformation of the silicone diaphragm, and the greater the output pressure of the sensor. So here you can see it. This part is a vacuum, which means it's a different pressure from the pressure here that is connected in the intake manifold. And as stated here, as the pressure fluctuates the diaphragm, it sends a corresponding signal. More on this later. And the second type of map sensor is the capacitive. The schematic diagram of the capacitive map sensor is shown in the picture below. The aluminum oxide diaphragm and the hollow insulating medium from a capacitive pressure sensitive element with a vacuum inside is which connected to the sensor hybrid integrated circuit. So I think this is more like for the PCB type of map sensor. There is a two types of metals inside, with this first one is the aluminum oxide diaphragm and the hollow insulating medium. So this is, I believe, this is like the Hall type effect of map sensor. You can pause the video to see each one of them. Okay. Insulating medium. 5 is the aluminum diaphragm, both of these. And 6, intake pipe pressure. Oh, okay. That's how you see it. More on the operations later on. After the sensor introduced the pressure of the intake pipe, the aluminum oxide diaphragm deforms under the action of the intake pressure, causing its capacity value to change. After processed by the hybrid integrated circuit, it outputs an electrical signal corresponding in the intake pressure. So more on this explanation later. Operation of a map sensor. Here we go. So first one is the semiconductor varistor pressure sensor. The semiconductor varistor pressure sensor uses the piezo-sensitive, sorry, it's really hard to pronounce that word, effect of semiconductors to convert pressure into a corresponding voltage signals, and its principle is shown in the picture below. So these are the sensors in the diaphragm, and each of them corresponds a different voltage regulation, sorry. And each of those are going to be sent in here. The number 2 is the amplifier circuit, which is the signal voltage. Be exact. This is the supply, and this is the ground. All of the information of these 4 resistors are then processed by this sensor and then sent to the ECU. And this is it in action. So as you can see, This one of the example I've shown also has an integrated temperature sensor. Go. So same principle again. Here you go. The semiconductor strain gauge is a sensitive element whose resistance value changes correspondingly when under tension or pressure. Attach the strain gauges to the silicon diaphragm and connected to a Wheatstone bridge. When the silicon diaphragm is deformed by force, each strain gauge is pulled or compressed, and its resistance changes, and the bridge will have a corresponding voltage output. You can see it here. This is the more simplified drawing of it. As the silicone chip moves, it sends a different signals because of the pressure increasing in the decreasing. I don't know. I mean increasing. Very sorry. Increasing, and then when the pressure drops, decreases, which sucks it. Okay. Capacitive map sensor. This is the next one. The capacitive pressure sensor uses a diaphragm to form a pressure-sensitive element with a variable capacitance. When the diaphragm is deformed by force, its capacitance changes accordingly. The sensor measuring circuit converts the capacitance change corresponding to the pressure into a corresponding electrical signal. Capacitive pressure sensors measurement circuits mainly have two types: frequency detection and voltage detection, as shown in the pictures below. Okay, next. Frequency detection type. The oscillating frequency of the oscillating circuit changes with the change of the capacitance value of the pressure-sensitive element, and the pulse signal whose frequency corresponds to the pressure is output after rectification and amplification. And the voltage detection type. The change of the capacitance value of the pressure-sensitive element is modulated by the carrier and AC amplified circuits, then modulated by the detector circuit and filtered by the filter circuit to output a voltage signal corresponding to the pressure change. Okay, so both of them almost has the same idea but difference in purpose. Specifically, the frequency detection type is more of a analog, and the voltage detection is more of a digital type. You can pause the video to see those, and that is all. Thank you for listening.